reason due to the suspension introduced in our model. Now, let us continue with rollover stability analysis, right? Rollover stability analysis. So rollover stability, when you say, it is like yaw stability, yaw stability is there is no understeer effect in your vehicle at critical speed. So if your vehicle has got an understeer oversteer effect, and your vehicle is at critical speed, you know what would happen. So your vehicle will spin about as a vertical axis arbitrarily. So that is what is unstable state and yaw motion that we have seen. For that to understand, bicycle model is sufficient. The moment you introduce your suspension, there is also an unstable state of a vehicle that would happen, or the vehicle will impend to get into unstable, impend to roll over, that's what it's saying. So the roll is permitted within some angle. There is a threshold value of roll of your vehicle body, of your roll, of your axle. So axle also rolls, though it is an instantaneous effect. At precipitation of your rollover point, impending state, you also have to account the roll of your axle, right? So the roll of the axle is because of tire deflection. So when it goes straight, no cornering, there is no lateral load transfer, the deflection in your tire on both sides of the wheels, left side and right side, are same. The moment there is a rollover because of cornering or side force acting, there is a rollover, the roll happens. What will happen? The tire deflection is what is responsible for the axle roll. And further, the body also rolls. There are two rolls that take place in your vehicle. So you have to account that, and you should find out what would be the threshold value of these rolls. And that would help you to design your suspension for its optimum value of roll stiffness of your vehicle, so that you can ensure there is always stable state of your vehicle, even though there is roll. So for that, let's look at this free body diagram to understand. Again, this I'm going to take it as a simplified free body diagram. Let me consider a flat road, and I have my axle represented this way. So now again I'm taking plane which is YZ plane through CG location, like that you can consider. So the left side two wheels are taken together, right side two wheels are taken together, and you define your roll center point with this kind of representation. So this point is your roll center, and your entire vehicle sits on this. So this rollover problem is more pronounced in the trucks, even at low speeds, right? Heavy trucks. In passenger car, it is very rarest phenomena unless and until your suspensions roll moment distribution is such that are so hard cornering, there is a threshold value of your lateral acceleration for an impending rollover unstable state, right? So if your vehicle goes to that lateral acceleration, which is again depends upon the roll of axle as well as the roll of your vehicle body. So such expression is what we are going to determine now. So this is your vehicle schematic representation. At that time, let's say this is the CG location of your vehicle, and the free body diagram is weight of this is acting down, and that's balanced by normal loads. Say this is FZL left side, and this is FZR. FZR. And let me define now for convenient the height of roll center from the ground as H1. We have defined in our previous analysis HRC. Please consider this as H1 and this as H2, and the CG height from the ground as H. This is what we always consider, right? So consider the same. And what is tread or track is what is this distance t along lateral direction. You measure wheelbase along longitudinal direction. You measure track or tread, it is called along the transverse direction, along the y-axis, right, in the vehicle. So now, in this free body diagram, when it goes straight and the deflection in both the tire, you see, is same. The deflection is, say, given by delta r. Delta r is the deflection, tire deflection. We will just see the same notation that I follow, what I have in my notes. Small r, it's not capital R, small r. The small r is what is tire deflection. Let's consider that later. Now you can see that what would be the two roles that I have defined. One is say phi 1. Phi 1 is the role of unsprung mass. Is the role of unsprung mass. So what is that mass? It's axle mass, axle wheel or. And this role is happening is because of due to what? Due to the deflection. Due to the deflection of the tires. Due to the deflection of the tires in the left and right. So this is. So if I have to account that, represent in my diagram, how do I draw my diagram? And see, it takes the right turn, and the deflection here on my left wheel axle, left wheel axle would be more than that of right. So I would have this tire height smaller compared to that of this. I'm drawing an exaggerated diagram. These angles are very small angle. So here what is happening? There is delta R equal on both sides. So at this stage, delta RL is what is delta R right, and that's equal to delta R. That's equal to delta R small. When there is no turn, the deflection equal in both wheels. But when it is taking a turn, since the load comes on this, the tire deflection here is more than that of tire deflection here. So this would reduce in diameter, and this would effective radius here is different than here. So this would become almost free rolling. So the deflection would disappear at the tip of the tipping condition, at the wedge of tipping. That means a rollover about the left wheel contact point, about this point. At that time, delta F is delta R is become 0. Here delta R is 0, whereas here delta RR become 2 times delta R. Delta RL become 2 times delta R. So this is what would happen on this side and this side with respect to tire deflection. With respect to tire deflection. So this axle here at the center and here at the center, you see there is small inclination. It's not a perfect horizontal, small inclination, and this inclination to the horizontal is what is phi 1. That's roll of axle due to tire deflection. That's what I defined. And you had the roll center slightly gone there. And here further here, so if I consider this is my vertical line, this is my vertical line, and now this phi 1 would be represented with respect to perpendicular drawn to the axle. That would be, I'm just exaggerating this for understanding what's happening. So this is that angle phi 1, right? Let me now put the vehicle body there. So the vehicle body now would be goes like this. Right? So the CG location which was initially here is now transferred here. This is my CG location now. At that point, I would have my forces like this. So what is this is centrifugal force. I write now MAY, where M is total mass of the vehicle, and this is W, down vertical weight of the vehicle. And now you see this, the role of this further from this. So this is phi1, right? So I have to write now where is phi1. So phi1 is somewhere here. It's a small angle. When this axle rotated, I have my CG location somewhere here, and then further roll of my vehicle body. This is there. So that roll is what is this? That is this given by this angle, this angle. So that angle is phi2. The role of relative role of phi with respect to the axle is phi2. And this angle is what is phi1. This angle is what is phi1. This is phi1. Phi1. So phi1 is roll. So what is phi2 now? Phi2 is the roll of sprung mass. Is the roll of sprung mass. It's vehicle body. Right? About what? About the roll axis. About this roll axis. About the roll axis. So with this understanding now, we can find out moment equilibrium about the point which is projected onto this. So here importantly, the free body diagram, what would happen to this normal load? It could be here. So I have here F is at L, F is at L, and here F is at R. Right, F is at R, and similarly here I will also have my lateral force developed. F is at L, sorry, Fy L, Fy left, Fy R, Fy R. So I take moment about this contact point O, which should be a midpoint of this thread. So I have here T by 2 and here this distance T by 2. So let me use the convention clockwise positive moment to write this expression. Sigma m about the point O, this is point O now, is equal to 0 considering clockwise moment positive. So now what is that equation going to be? F is at L into T by 2 minus F is at R into T by 2. So T by 2, let me take it out, and that is moment by these two, and this lateral force won't participate. In fact, that won't be disappear. That would disappear as it is transferred to this CG location that we have seen right in the previous discussion as well. So now I have here two forces, MA, Y and W. So now the moment expression to take, again let me just draw this diagram for you for convenient. What are these heights, right? So for that the H1, so I should consider from here this height till here. Initially when it is straight, this H1 as it is, right? I can draw that here only, this diagram. So this is my vertical. In this I have first this rotation, axle rotation due to tire, that's phi1, And let me just extend that line further like this. And then from here there is a roll. So let me extend that here like this. That's what is happened. So there is an angle phi 1, that's this angle. This angle is phi 1, this angle is phi 1, and this angle is phi 2. This is phi 1, this is phi 2. And this height here is h1. And this height from here to here. So this height is now h2. h2. And see, this is angle phi 1, this is angle phi 2, this is angle phi 2 here. This phi 2, if I draw perpendicular here, I can measure this distance here. These distances are required because I have this is my CG location. At CG location, I have these two forces. So I require this moment arms when I take a moment. So this is what is that heights helps you to find out now. And I can write down this equation. So M A Y minus sign is because this would create about this point is counterclockwise moment. I follow this convention clockwise positive. So MAY into what is my moment arm, this height. So this height would be now, this h2 is now this length, right? It's not h1 plus h2 I will write. So this is now height is h1 cos phi 1, h1 cos phi 1, because this is rotated. So when I project this, when this is rotated, h1 height is reduced. See, this is rotated by this height. Right, this is phi 1. So what is this net height now? It's h1 cos phi, h1 cos phi plus h2. Now this h2 also further rotated by angle to the verticals phi 1 plus phi 2. So it is h2 cos phi 1 plus phi 2. So this is what is the moment arm for that moment. Then third moment is due to the weight of the vehicle. It's minus W into this width. So that would be h2 sine phi 2 cos phi 2 plus h1 plus h2 sine phi 1. So this is what is the momentum now in this case. This is what is the momentum. How does it come? Is very clear here. So this height, this distance is h1 sine phi 1. Whereas this distance here now, this would be h2 sine phi, and its projection on that is cos phi. So this is h2 sine phi 2 into cos phi 2. So this sum is what is this distance, and that's what is written here. So this all sum, this three moment sum is equal to 0 at equilibrium, right? At dynamic equilibrium. So this is equation number 1, and we are very much aware that though here I have drawn this angle phi 1, phi 2 slightly exaggerated to understand the phenomena, and they are very small angles, right? Phi 1 and phi 2 are very small angles. Then what would happen? Equation 1 becomes, this equation 1 becomes f is at L minus f is at R into T by 2, that's equal to, here this is all modified as MAY. So this minus 2 minus I'm taking on the other side to become positive, H1 plus H2 plus NG into H1 plus H2. So this is sin phi is phi 2, cos phi 2 is 1. So H2 phi 2 here, H1 plus H2 sin phi. So this is sin phi become sin phi become sin phi 1 become phi 1. So H1 plus H2 into phi 1, and here it's H2 phi 2 plus H2 phi 2, and this all in single bracket. And this is my equation 2. And if you look at here, the contribution that comes from this is very small, but it cannot be neglected. We will see that accounting that. So this term contribution is very small. If you consider that, you neglect this, and then you can equate for an engineering analysis, you have to account that. We will do that later. But if I neglect this, then it becomes very simplified expression. F is at L minus F is at R into T by 2 is what is simply MAY into H1 plus H2. This is just looking at your this diagram itself, looking at this itself. So at the start of roll, this is very small. I take this H1 plus H2 as it is. So this lateral force MAY into H1 plus H2 plus this roll due to this. So the roll, see here, here this phi1 is neglected because this tire deflection due to that is very small. The second term I neglected. Then it is only through the body roll that we consider, right? So this expression, so I can just get this from this. What is I'm interested in this lateral acceleration. Lateral acceleration value, I can rewrite this as this. So during the turn here, you have to see during the turn, at the time of tipping is only I am interested in. At the time of tipping. Tipping about what? Left wheel, right? Left wheel contact the ground. So at the time of tipping, I know that the right side F is at R is going to be 0. The reaction at the right side wheel is 0. So what would happen in this left hand side in this equation? F is at R is 0. So I would have F is at L entirely was going to carry the total weight of the vehicle, which is mg. Entire load of the vehicle would come on this axle wheel. So at that stage, what is happening? Both this F is at L reaction and mg has become collinear. That become collinear, and they balance. And that is at the time of tipping. That is the impending state. The further goes when it is not collinear and mg goes outside this normal, then there is rollover has to happen. That is the edge point. That's a condition. So then what would happen? I would have my equation. So let's call this equation as 3. So this equation 3 would become this F is at L minus F is at R is simply mg T by 2, that's equal to M AY into H1 plus H2, right? So this M goes out. I would have now G T by 2 equals AY into H1 plus H2. So let me rewrite this expression for lateral acceleration normalized by G, that is AY by G is taken out. Is going to be T by 2 into H1 plus H2, where H1 plus H2 is CG location from ground 2 times H. So this is a thumb rule. So what is that you get from this expression number 4 is, if I have my truck, heavy truck, I know what is my tread, what is CG location height, then T by 2 times CG location height is what is my limiting lateral acceleration normalized to G. Right? So limiting value of maximum lateral acceleration that can be felt just before rollover. So here what is that I have got is this limiting, this is limiting value of lateral acceleration or maximum AY by G that can be felt just before just before the rollover, right? So if you look at this value for typical trucks would be AY by G, very small value only that would happen, right? It will be equal to 0.18 to 0.3 for trucks, 0.3 for trucks. Whereas the same, if you take for a passenger car, that value is more. AY by G value would be around 0.8 for cars. If it is SUV is 0.8, if it is sedan class 0.8, if it is of SUVs, sport utility vehicle, then this value will be further reduced because the height of the vehicle is more. So maybe 0.7 or 0.65, right? So this is what is the limiting value. It's an industrial practice that by a vehicle looking at the dimension of the vehicle, tread and CG location height, one can say that what is the limiting lateral acceleration during cornering in order to avoid rollover in the vehicle, right? That's very important. Any value CG height is not elevated, that problem won't be there. But the CG location in a vehicle is from the ground at an elevated position, generally of a high height vehicle in trucks or SUVs that you can see. Whereas in race cars, you see that the height of the vehicle itself is very small. So there, unless and until it hits and then it is very hard cornering, the vehicle is of oversteer tendency. Your roll movement distribution is more in the rear axle than that of the front axle in race cars. Then there will be a chance that the vehicle rollover takes place. Otherwise, if there is no hit of other vehicle on one vehicle, the rollover in race cars is very not that pronounced. Rather, it would be spinning about vertical axis. Anytime the stability of your racing car is loose by observation, you can see that it spins about vertical axis, right? Whereas the trucks are rolled over to fail its stable state. So this is but for design of your suspension, which is very critical, it is not only designed for your lateral dynamics, also designed for your vertical dynamics as well as for your longitudinal dynamics. There are other effects of vibration, isolation, and so on. One has to be optimized way to design your suspension design. So if that is your intention, you cannot neglect the second term in our equation number 2. So I should consider that as well. For more engineering analysis, we have to consider that as well. So let me write now equation number 2 and proceed. And those who have got class can proceed for the next class. Let me just to finish this lecture in another 5-10 minutes, and later on we can listen. I have just downloaded your attendance sheet. And today's attendance is very less. Okay. Why? So, right? Okay. If you have a lecture, you can proceed. I just finish this lecture part, and then you can revisit this back. If you have to account the second term, what would happen? So there would be another 5 minutes lecture. I just complete it. You may proceed for the next class. So to consider the second term also, the equation 2 would become now. Let me write that equation 2 will be mg t by 2. So this is at the time of tipping, right? At the time of tipping. At the time of tipping, mg into t by 2 is what is going to be mg ay by g. See, I have made ay as mg into ay by g into h1 plus h2 plus mg into h1 plus h2 into phi2, sorry, phi1 plus h2 into phi2. So this is equation number 5 now. So in this equation, I can write now I'm just going to manipulate this equation so that I can express the threshold values of the permissible value of phi1 and phi2. Yes. So for that, let me just divide this entire equation by mg on both sides. So it's going to be t by 2. On this side, it is going to be ay by g into h1 plus h2. And here mg goes out, so this is going to be h1. This is plus h1 plus h2 into phi 1 plus h2 phi 2. And further, I just want to bring this h1 plus h2 here. T by 2 h1 plus h2. So this side it's going to be ay by g plus phi 1. So here also I have taken h1 plus h2 out, so it's going to be phi 1, and I call this phi 1 with the threshold value of t, right? Plus h2 by h1 plus h2, because this h1 plus h2 term taken out. So this their quantity into phi 2t, threshold value of this. So now what is my interest is this ay by g. So ay by g is what is maximum permissible lateral acceleration to avoid just at the time of tipping, or just before the time of tipping. So this is going to be t by 2 into h1 plus h2, which we have just seen now previously. And now that value is subtracted further by these terms, phi 1t minus h2 by h1 plus h2, phi 2t, right? So this is equation number 6. See, look at now phi 1t and phi 2t. Phi 1 is the roll of axle due to tire deflection. Phi 2 is roll of the vehicle body, right, relative to axle. So now the question is, how do you get the values of phi 1t and phi 2t? These two values, the roll of axle and roll of this, is what you have to find out. For that only, let's define the following, right? So what are those? Let us define now these terms. Delta R, let delta R, delta L, delta R, delta small r is what is the radial deflection of the tire. Radial deflection of the tire. And CR, C subscript capital R, radial stiffness of the tire. Radial stiffness. See, this stiffness from cornering stiffness we should differentiate. C subscript capital R is the radial stiffness. That is vertical stiffness of the tire. You take a tire and you load it. What is the deflection that you measure is what is this delta R, and that stiffness load per deflection is what is your radial stiffness of the tire. So let's define this in meters, this in Newton per meter for SI units definition. And of course, you have already defined what is K phi is roll stiffness of the body, and that's given by Newton meter per radians, right? So if I define this like this, I can go further explaining this. Considering the tire deflection, phi 1 can be found during the straight motion as this way. What is that? During straight motion, and there is no load transfer, I would say that delta R tire deflection would be same as delta RL is delta R. Right side and left side tire deflection is same. And the CR into delta R is what is my FZ L is equal to FZ R. So this CR into delta R, which would be equal to FZ L, that's equal to FZ R. Normal loads in the tire. So now I can write this like this. This is delta R. This is delta R, right? Now you can also write this as change in delta FZ. CR into delta R as change in delta FZ at the time of tipping. At the time of tipping, CR into delta R is going to be delta FZ. Delta FZ. Delta FZ. That's equation number 7. This delta FZ is what? Of course, delta FZ is FZL minus FZR. At the time of tipping, FZR is 0. So FZF is going to be FZL. That's the entire weight mg. Correct? This is all at the time of tipping. This is at the time of tipping. That's why I can rewrite this expression as CR into delta R as delta FZ. Delta FZ. So I can rewrite this as for phi 1 T to get 2 times delta R by T, right? How do you get that? This way. This expression. Phi 1, threshold value of this, the roll of axle is given by 2 times delta R by T. 2 times delta R by T. 2 times delta R is what? At the time of tipping, you have this threshold value of phi 1, and that would be is delta RL. Delta RL, right? Left hand side, whatever is the deflection, that is 2 times delta R by T, right? So in this delta R, I should substitute. So how does this come? You understand, right? Because when it is straight delta R on both sides, one side is lifted from the ground, the total deflection becomes double. That's why 2 delta R by T, and that is the deflection in left axle wheel by T. So I can rewrite now this expression as this way. So delta R, I am going to replace it with this delta FZ by CR. So if I substitute that, it's going to be delta FZ by CR into T, right? CR into T. So the delta FZ is what? Is delta FZ is FZL itself. FZL itself. FZL itself by CR into T. So FZL is nothing but mg. So mg by CR into T. So that's equation 8. So what is the roll angle of threshold value is the weight divided by CR, vertical stiffness of the tire, into T. This is equation 8. So considering now the body roll, considering now the body roll, what would happen? K phi into phi 2, K phi into phi 2, right? Because this is that roll of vehicle body reference to the axle. So that would be equal to MAY into H2 into cos phi1 plus phi2 plus mg h2 sin phi1 plus phi2. So I can write once again k phi into phi2, that's equal to mg h2 mg may into h2. Well, these angles are small, and I can get cos of angle is 1 and sin of angle is sine angle itself. So this is going to be mg h2 into phi1 plus phi2. So there's phi2 here, there's phi2 here, so I have to group them to get threshold value of phi2. So I will take this term phi2 on this side, so that's going to be k phi minus mg h2 into phi2, and here I have m ay. So I wanted to write in terms of this ag. So ag, sorry, ay by g, right? Ay, that's not g, ay by g, ay by g, and I divide by g, multiply by g, so this has become mg h2, mg h2 plus here I have mg h2 into phi1 alone, mg h2 into phi1 alone. This term mg h2 phi2 is taken on this side. So further this can be reduced for now the expression of phi2. So phi2 threshold value would be now ay by g threshold value into mg h2 by k phi minus mg h2 plus mg h2 by k phi minus mg h2 into phi 1t. So phi 1t is already there, mg by cr into t. So if I substitute that again further here, phi 2 will be ay by g t into mg h2 by k phi minus mg h2 plus mg h2 by k phi minus mg h2 into mg by CRT. This is my expression, 10th expression. So equation 9 is this. Equation 9 is this, equation 10 is this. So equation 8 and 10 gives you now the threshold value of roll of axle and body respectively. And now again further to simplify this, let's define this normalized values. So CR star now, instead of radial stiffness, I take CR star is normalized by this way, CR by mg by t. So the weight by t ratio, CR by this is what is now CR star, and instead of k phi I have k phi star, and that's going to be k phi by mgh2. So if I introduce these two normalized CR dash, CR star and k phi star, the expression would now differ like this. So what is that objective? See, this I defined. Also I have now equation 8 and 10. So substitute equation 8 and 10. So put equation 8 and 10 in equation 6. So equation 6 was our equation for threshold value of lateral acceleration. What was it? Equation 6 was this: ay by g into, ay by g threshold value would be t by 2 into h1 plus h2 minus phi 1 t minus h2 by h1 plus h2 into phi 2 t. Right, in this I have to substitute now equation 8, that is phi 1 t, and equation 10, that is for phi 2 t, with this normalized CR star and K phi star. If I do that and continue, I would end up with this equation. I leave it to you to work out. That would be AY by G will be given by special value will be given by T by 2 divided by H1 plus H2 plus H2 by K phi star minus 1. Minus 1 by CR star. So this is the final expression of lateral acceleration. So here I have K phi star and CR star, right? Now let's call this the equation number 11. So what is the use of this equation? Suppose if I have data given for a vehicle, for a truck, say the load is given and the tire stiffness is given, what is this track P value is known, H1 value, what is roll center height from the ground is known, H2 value is known, that is from roll center to CG location, all are known. You can determine the roll stiffness value, K phi, optimum value of K phi can be obtained. That's what is design of the suspension spring. That comes from the suspension design, right? So optimum value of K phi can be determined from this equation that accounts for suspension design. So when you go for suspension design, what is that? The stiffness of the suspension is primarily important, and that depends. That is going to influence the roll stiffness of the body. So the optimum value of roll stiffness that's necessary to meet this threshold value that can be obtained by this. So if these data are given and I vary my K phi star value, see K phi star value here is 1, what would happen? That's going to be 0, H2 by 0, anything by 0 is infinity. So if this is infinity, this term goes and I get some value here, right? So if I keep changing AY by G value is 0, K phi value is 1, K phi star value. K phi star value keep increasing, I would have my plot. So this plot for the given vehicle, you can find what is that maximum value from T by 2H. So you know that this value, if my vertical axis represent AY by G value, so this value would be corresponding to what? T by 2H. And the variation of this lateral acceleration developed, if I express as function of K phi star, what is there in my expression number 11, right? Then I would have my values goes like this. So here K phi star is 3, 5, 7, and so on. 7, 9, 11, 13, and so on. I would have something like this. I plot, and this will be asymptotically going here. So there will be some, what is the maximum value that's possible can be designed from this, right? So I can get for, see this will be flattened at some time. So at that point I should design. Otherwise what's happening, this flatten, it goes like this, it takes longer time. So where it is almost closer to zero slope, this curve, and that corresponding K phi star value I should take, and then from there I should get my K phi, and then I should decide what should be my stiffness Ks. So that is what is you get it from here. If you do not consider like that, I do not know what would be the value of K5. I know the lateral acceleration that should be limited by this value without considering the second term, sorry, T by 2G. But if you have to consider the second term, you get an expression where your lateral acceleration is related to threshold value of roll and axle roll at vehicle body. In turn, that relates to roll stiffness and roll stiffness. And that roll stiffness value to get, you should have this variation plot from this expression, and that would help you to get an optimum value of your K5. So when this is almost flat, and you should take that minimum value. So if I take here this value around 3, 4 K5 star, that's not the correct value, because that limiting only this is the lateral acceleration. I have to go to this, but I should not go with the higher value. So accordingly, I should decide my value of K5 star, and hence K5 star you have defined as that's equal to what? K5 star you have defined as K5 by mgh2. K5 by mgh2, correct? You know K5 star is K5 by mgh2. So this total load, and h2 is the height from roll center to the CG location. So if I plot this and then I get my K5 optimum value, and that K5 value if I equate, I will know what is my K5, and this K5 is what is half into Ks into S square. So this Ks is what is the spring constant of the suspension. So this is how you can decide your suspension, design your suspension springs. So with that, let us conclude today's class. What we have done is, from our previous study where we have not considered the effect of suspension in our lateral dynamics, now when I account that, I have two important observations. One is my vehicle tendency get influenced by suspension design. So you have seen there is a second term of understeer gradient getting added with my bicycle model, and that is due to lateral load transfer. There are two mechanisms. One is load transfer due to transfer of lateral force to the roll center in the axle. That's an instantaneous effect which is independent of the roll of the vehicle body. Another effect is the vehicle body roll itself. That's what we have seen in the first part of suspension design. And then to study our critical lateral dynamics, study of stability point of view, what would be my optimum design of suspension to do? I require to calculate two rolls. One is the roll of axle and roll of body and the threshold values, and that helps us to find out what is the threshold limiting value of lateral acceleration, maximum value of lateral acceleration permissible just before the rollover of your vehicle, right? So this is all sufficient in this part, and in the next class let us look at some more design aspects. What would be the effect of camber, what would be the effect of tractive force. Instead of steady state motion, if I have tractive force also that comes into the tire or interaction, what would be the changes? And there are something called the roll steer effect due to NVH compliance bushes properties. There are so many other design aspects. So let's account them and look at it in the next class, and that completes the next module, and we will be left with only the vertical dynamics part, and that we will look at it after we resume back a week break again. Week break again is given to all students classes, and the next week because of first year admission, witty entrance examination, we all faculty also have been assigned duty for that. Meanwhile, I would also, if time permits, during that week, maybe in the evening hours, if I do not have, every day we have an invigilation duty. During my free time, I would try to organize your review for your J component, whatever you have submitted, let us have a discussion to further improvise that. So with that note, let me stop today's class in case you do not have any further questions. Right? Yeah. Let me download your attendance. I'll stop recording.